This is AP Calculus AB Unit 6, covering integration and accumulation of change. So first we're going to talk about what accumulation of change means in a graphical calculus setting. And so the area between a derivative function, that's the rate of change function, and the y or x-axis represents the net change over any interval. So the area in the green shaded figure represents the change between the x value of 0 and the x value of 4 in the original function, assuming the red value is the derivative. So one way to calculate that, because it's hard to just calculate this awkward shape, is you use, they're called Riemann sums. They use rectangles, which have a simple formula, obviously, to calculate the area. So you have one where you divide into however many sections you want. In this case, each one is divided into 4 sections. So you would take, and this is the same function from earlier, you would take the 4, in this case we're doing the area from 0 to 4, dividing it into 4 sections. So we're starting a triangle, a rectangle on the left end of each point. So this is a point at 0, at point 1, at point 2, and at point 3. And then you can find the area of a rectangle for each one. The base is going to be 1, and then the height is going to be the value of the function at that point. The second one is going to be the midpoint formula. So same thing, split it into 4, except this time for our y value, we're going to take the midpoint between the start and the end of the rectangle. So in this case, we're taking the point, instead of at 1, 2, 0, 1, 2, and 3, we're going to take the point at 0.5, 1.5, 2.5, and 3.5. And then predictably the last one is using the right. Same thing, same rectangle setup, except now we're taking the point at 1, 2, 3, and 4. Depends on the case what your function is. Some of them might be better, some of them might be worse. Usually if one underestimates, another's going to overestimate. And yeah, so this is the analytical formula of it. The length of your interval divided by your number of rectangles is going to get you your base formula, times your y value, your second y value, your third y value. Should be something you can visualize in your head depending on which one you're doing, or you can just draw a picture and you can find the area that way. So this is the power of Riemann sums as you change, if you don't just use one solid number. So we're using the function x squared, and we're going to find the area under the curve from 0 to 3, or get an approximation of it. Now, normally what we were doing, we did like 3, 4, 5. That's normally what you're going to do in class. But should be easy to see. As you get closer and closer, they'll limit, if you want to say, as the number of rectangles approaches infinity, you're going to get closer and closer, but obviously still not actually there, to the actual value of the function. This is a nice thing to play around with. You can see, in this case, the function is increasing. So if I put my sums with my rectangles on the left, it's going to underestimate. You can see there's area under the curve I'm not counting, because the function is increasing as I'm counting. And then in the same way, the function is increasing. So if I put my rectangles on the right, I'm counting area that's not actually part of the function. So in this case, if a left sum is going to underestimate and a right sum is going to overestimate, if I wanted the most accurate, I would probably need a midpoint sum. You can see I count some that's not part of it, and I don't count some that is part of it. Probably the most accurate way to measure this. But the more precise way is by antidifferentiation, indefinite integrals, indefinite integration. Integration is the biggest part, other than derivatives, I'd say, in calculus. It's the opposite of taking the derivative of something. you're assuming that the function you're given is the derivative and you're trying to find the original function, is usually the way I think about it. But it can also be used to find the area under a curve if you take the derivative and then multiply by the interval. Now these are your simple rules. You're going to have to learn them. They're going to come in handy. The same way when you take the derivative of something, if you have a function plus another function, if you had x squared plus 2, you could take the derivative of x squared plus the derivative of x the derivative of 2. And this way you could say if you have the derivative or the integral of a plus b, you could do the integral of a plus the integral of b. If you have a constant number, the integral of that is going to be x times that constant. If you have x to a power, the integral is going to be x to the power plus 1 divided by the power plus 1. And as you go with these, you'll see that if you're not sure, you can just take the derivative of your answer, and if you get what you were given, then you did it right. Then last one, the derivative of x is going to be x squared over 2. And then with any integral you take, the most important part, you have to add plus c, because you don't know if I took the derivative of x squared plus 2 is going to be 2x, or if I took the derivative of x squared plus 100, it's also going to be 2x, because anytime you take the derivative, you take out any constants that were added. So this plus c just means there could have been a constant in the original function that I'm taking the integral of, but I don't know. Biggest thing you need to remember, all of these rules, same as your differentiation rules, they're going to become second nature as you're using them. It just takes practice.